Hello, welcome to this video on inductances. We'll solve two examples on inductances to cover the classes that we missed in the week in this week due to the coronavirus closure. I will try to go over two examples in detail, and the examples on inductance are very important because you're going to see for sure one question on that in the final exam. We use this expression for inductances often in many applications. Let's now see how we're gonna handle these inductance examples. Okay, from the videos that you have seen, the lecture videos, you have seen the method for calculating the mutual inductance. So what's happening? You usually have a coil or a structure that creates magnetic field. Okay, we have here this first coil. There's a current in it called I1, and we have this second coil here. It can have a current called I2. So when the current flows in this coil or this loop or whatever structure it is, it's gonna create a magnetic field everywhere in the space. We call this magnetic field H1. And we can get from it the corresponding magnetic flux density by multiplying by mu naught if it's air. If it's not air, maybe there is some steel or something here, multiply by mu of that steel, okay? Now, this flux that's created by this current I1 links to the second loop. You can see it goes through the area, the cross-section area of this loop. So if this cross-section is circular, okay, so if I draw it, maybe I can draw it like that. So if this is, take a look at the second loop, if the cross-sectional section here is circular, then the magnetic field is actually going through that circle here. So this will be the magnetic field resulting from the first coil, and it's going through the cross-sectional area of the second coil. So it creates a flux, okay, and we call this flux psi21. This is a flux in the second coil due to the current and the magnetic field of the first coil. Okay, so I can calculate psi21. Psi21 here is simply the integral of B1 over the area of the second coil. So it is the integral of B1 dot ds. Once you have found psi21, we calculate something else called flux linkage. And flux linkage is simply the flux. If you have turns like this, it's simply the flux multiplied by the number of turns. So the reason we have to calculate that is that if you calculate the flux here, psi21, it talks only about one loop, one turn of that loop, one turn. But if you have multiple turns, this means that this flux psi1 goes through the second coil a number of times. So you have to calculate this flux linkage. It links it a number of times. So once you have the flux linkage, we say that the mutual inductance M21 is lambda 21 divided by the current I1. This recipe for calculating the mutual inductance is very similar to the Q method or the V method we use to calculate the capacitances. So here you have to assume a current, get the magnetic field intensity, get the magnetic flux density for the first coil, get psi21, the flux going through one turn of the second coil, and then get the flux linkage, which is simply psi multiplying by the number of turns, if you have a number of turns. And then you see that the mutual inductance is lambda 21 divided by I1. Why do we need to calculate this one? Well, the reason we need to calculate that is that if you connect here on this side an AC source, okay, an AC source, it's a source that's varying with time. So the current I1 will be also varying with time. H1 will be varying with time. B1 will be varying with time. Psi will be varying with time, and lambda 2 will be varying with time. The voltage that you can measure on the other side, due to the time variation of the first coil, is directly proportional to this M. So you can simply say here in a situation like this that the voltage you're going to be getting is M21 di1 by dt. Okay, if this is kept like open circuit like this. So the mutual inductance tells you the ability of the time variations of the current in the first coil to create a voltage in the second coil. And so M21 is really related to Faraday's law, which we're going to be talking about very soon. Faraday's law shows that time varying magnetic fields give rise to electric field, and that electric field is what creates this voltage difference. Okay, so we'll be talking more about that next week in the time varying part. Okay, so someone else will ask me, can I do the same with I2? Of course, you could start by assuming a current I2, okay, and then you calculate the magnetic field H2 everywhere in the space, calculate the magnetic flux density B2 everywhere in the space, integrate B2 over the cross-sectional area of the first coil to get psi 1, 2, multiply by the number of turns of the first coil to get lambda 1, 2, and then you say that M12 is equal to lambda 12 divided by I2. These two numbers should be the same. Should be the same for most reciprocal circuits, and most media that we talk about here are reciprocal. It's going to be the same. M12 is going to be equal to M21. But in some applications, it's way easier to calculate maybe M21 than calculating M12, as I will show you. So you have, when I give you an example inductance, you have to ask yourself, which one is easier to calculate? Which one I can do analytically, because you'll be doing this in an exam. Is it M12 or M21? Okay, so we'll start now to show you. This is the theoretical background of this part. You have to keep this one in mind for your questions. And now let's start take a look at two questions that we are going to use calculate mutual inductance for them. Okay, our first example here is a toroidal coil. So we have a toroidal coil here. So you see it's a toroid, and the toroid, the core of it has a rectangular cross section. Okay, so the core, if you take a cross section here, it's not circular, it's rectangular. These are tightly wound turns, but I'm just, of course, I cannot draw it exactly here. But if you take the cross section actually at any part, it looks like a rectangle. Okay, you can see this width here is equal to D. This width here is equal to D. This radius from the center to the inner part is A. The radius from the center to the outer part is B. So this one here is A, and this one here is B. So this is really a cross section of the toroid. And the expression for the magnetic field of the toroid is something that you should have in your cheat sheets. This year maybe we'll see, you may not have an in-person exam, but if you have an in-person exam, you must have the formula for the magnetic field of the toroid handy. Now this toroid coil cuts through a rectangular coil. Okay, so this toroid cuts through the plane of rectangular coil. So you have the current I1. The current I1 will create a magnetic field H. The magnetic field H will create a flux, magnetic flux density B1. B1 will cut through this area. Okay, and then it's gonna create psi to 1. And then this psi to 1, no one said anything about a number of turns here. So this simply say it's square coil, so we assume that this one has only one turn. So the flux linkage in this case, lambda to 1 is equal to psi to 1. And here they ask us to calculate the mutual inductance. So the procedure is, start by assuming current I1. You can keep everything symbolically if you want. You can assume I1 to be 5 ampere, it doesn't matter. Everything is going to be scaling up if you increase I1. Assume I1, get H1, get B1, get psi to 1. Psi to 1 is simply, you can see this magnetic field, it's cutting through the plane of the coil. So it's creating a flux through the plane. So this flux is psi to 1. Now, because this has only one turn, then it links through it, that flux link through the second coil or the rectangular coil only once. The lambda to 1 is equal to psi to 1. So whatever is simply to do all this in math and start to get an expression for the mutual inductance. Now, someone may ask me, why don't you assume I2 and get the mutual inductance? You can, of course, do that numerically. Here it's very difficult to do it analytically. The reason is this coil here, okay, creates a magnetic field. This magnetic field creates a flux. It creates a magnetic field H2. I'm gonna call it H2. It creates a magnetic flux density B2. This B2 goes through every turn, but the expression is very complicated. Psi in every cross section is different. So you have to do it numerically for every cross section to get different value, and then in that case the psi may not be the same here. What is going through this turn is different. What is going through this turn it's pretty complicated. You can do it numerically for sure. You can do it numerically, and you can get the total flux linkage. You can see the flux linkage is the sum of all the fluxes through each individual turn. You can do that, but analytically you can do that in an exam. Okay, so for this one we know we're going to focus on the easy part. Assume I1, get H1, get B1, get psi to 1, get lambda to 1, divided by I1, and you have the mutual inductance. Okay, we move forward. The expression for the magnetic field of the toroid is this one here. So it tells you that the magnetic field of the toroid exists only inside the toroid, and it is in the phi direction. Okay, it's in the phi direction, and is directly proportional to the current. So whatever current is flowing, you increase the current, the magnetic flux density becomes stronger. It's the linearly proportional number of turns. You have 100 turns, 200 turns, whatever. Mu naught is the permeability of the medium. Here no one said anything about mu naught, so we're going to assume about using different material than air, so we're going to assume that this is air. Rho is the radius from the center. So here if I measure this distance, this is rho from the center. Rho here is equal to A, rho here is equal to B. So rho changes from A to B. So the magnetic field is stronger at the side here, at the inside here, okay? It's stronger at the inside here, and it gets weaker and weaker as you go to the outside. So, but it is simply completely localized within the volume of the toroid. There is no magnetic field outside. Now we know that. Now remember that this toroid here cuts through the area of the coil, okay, of the coil. If I want to take a look at this cut here, because the cross-sectional area of the toroid, is rectangular, the cut the cut will look something like this. Okay, this inner radius is A, this outer radius is B. So this is here is this is from the center, this is A, and this from the center, this is B. Okay, and we agreed that the thickness of this here is D. Okay, so this thickness here on this side is D. So I want you to try to imagine that this toroidal coil has a rectangular cross section. So when it cuts through the plane of that rectangular coil, is gonna create a cut like this. This cut goes from A to B in the rho direction, and it goes distance D in the Z direction. So I want to calculate the flux linkage, the flux of the first toroidal coil that's going through the area of the second coil. We have to carry out this integral. Okay, notice this integral, we're integrating B1 over the area of the second coil. But remember, the flux is only localized in the cross-sectional area. So this one crosses here in this area, and it creates this cross cut. So the integral, even though in the beginning I can simply say that this integral over the complete surface of the rectangular coil, but because there is no flux outside, the flux is only localized, and it exists only in this volume here. So the flux is only in this direction. Okay, the flux exists only inside the toroid. Okay, it doesn't exist outside. So I don't really have to carry out the integral over the complete area of the rectangular coil. I will carry out the integral over this small part from A to B and from 0 up to D. And this is why the integral here became ds became d rho dz a phi, and the integral, I'm integrating over rho from a to b, I'm integrating over z from 0 up to d. So keep this in mind. There is no magnetic field here. There is no magnetic field B1 here. There is no magnetic field B1 here. There is no magnetic field B1 here. It only exists in this part where the toroidal coil cuts through the surface of the rectangular coil. This is why I have these bounds here. This integral is very easy to calculate. The integral of dz will give me z, so I multiply by d. The integral of 1 over rho is ln rho. Put upper limit minus lower limit, you get the ln of b over a. So this is psi to 1. How many turns does this rectangular coil have? No one said anything about multiple turns, so you have to assume it is only one turn. And when you assume that, a lambda to 1 will be equal to this number here, which is psi to 1. Okay, so as I said, only one turn for the rectangular coil. The lambda to 1, which is flux linkage, is psi to 1. This means that the flux goes through the rectangular coil only over one turn. So I have that. Now, by definition of the mutual inductance, M to 1 is lambda to 1 over I1. You're gonna get this one here. I1 disappears. And the inductance, by the way, is a number. It can be 0.4 millihenry. It can be 0.3. In this case, actually, it can even be negative, because depending on the direction you take for calculating the psi, the M21 could be negative. Okay, so mutual inductance can be negative. Self-inductance is always positive. So this is something to keep in mind as well. Now, as I said, you could have started by assuming I2, calculate the flux through every single turn of the toroid. This is going to be very hard to calculate. All these fluxes to get the flux linkage, and then divide by I2. You are going to get exactly the same value that you get here. But you can't do that analytically. You have to do it numerically. And some of you in the 4th year, I know they needed to design very complex coils. They have to go back and calculate the magnetic fields from basic principles and calculate the inductances and so on. Okay, now we move to have a second example. We have here a very long rectangular loop. So these two wires are part of a bigger circuit, but this bigger circuit, you can assume that one side here is in infinity and the other side here is in minus infinity, so we don't see it. Okay, there's a current I1 goes in the circuit this way, it comes back this way. The separation between these two is A. And then at a distance B from this infinitely long rectangular coil, you have a much smaller coil. It has a width of h and a length of l, and it has n turns. And what they are telling us, they are asking us to calculate the mutual inductance between these two. So if you have a current I2 passing in this coil, it's going to create a magnetic field H2 everywhere in the space, and it's going to create a magnetic flux density B2 everywhere in the space. And this magnetic flux density, you can simply calculate its flux through the area of the rectangular coil. Okay, you can do that. But of course, this is going to be very hard to calculate. Why? Because this coil is infinite in extension. So you can't do that analytically. You have to do it numerically. And maybe you don't have to do it, of course, from infinity to minus infinity. Maybe say you're going to do it from 10 meters this way and minus 10 meters this way, depending on the application. The easier thing here, the easier way of doing it is not to do that. Is not simply to assume I2 and get H2 and B2 and the psi 1, 2 and lambda 1, 2. Rather, assume a current I1, and then from I1 try to get the magnetic field H1, and so there will be a magnetic field H1 created. You can calculate it. So the magnetic field H1 will be all over the space. Okay, you can calculate it. Okay, and from which you are gonna get B1. You're gonna calculate the flux going through this small area, which we call it psi to 1, and then get lambda to 1. Notice that here you have N2 turns. Then lambda to 1 will be N2 multiplying psi to 1, because this flux here goes through the smaller coil N2 times. Okay? And then we can calculate the mutual inductance. So how do I get the magnetic field of this infinite coil? Well, I can treat each one of these two wires as an infinite wire, and I have the magnetic field of an infinite wire. We derive that together in class. It's I over 2 pi rho a phi. So this is something we can do. Okay. So the procedure is find the magnetic field resulting. Assume a current I1 here. Find the magnetic field resulting from these two wires, and they are separated by distance a. Calculate the magnetic field flux density B here at every point on this coil. Calculate its total flux, which you're going to call it epsilon 1. Multiply epsilon 1 by N2 to get the flux linkage, lambda to 1, and then divide by the I1 that you assumed. Okay, we get started. This current here, if you apply the right hand rule, you will see that at every point in this coil, it creates a magnetic flux, magnetic field H1, and the magnetic flux density B1 that is in the Z direction. If you see that its current going this way, then the magnetic field is coming out from the page, and this is the direction Z. Then the magnetic field at every point here is Z direction. The distance between this wire and this wire here and any point inside this coil, I'm gonna call it B plus Y. Y, its 0 is here. Okay, so Y goes from 0 up to infinity. So the distance between this wire and every point inside this coil, this smaller coil, is B plus Y. And the magnetic field it creates in Z direction. Let's talk about this other wire. If you apply the right hand rule, you will see that the magnetic field resulting from this wire is going in the negative Z direction at every point inside on the surface of this coil. Okay, and the distance between this wire to the coil is A plus B plus Y, and Y is a variable depending on where you are calculating the field. It is 0 here, and it is H here. Okay, then this is the expression for the total magnetic flux density resulting from these two wires. You can see this is what we call rho. Rho is simply for the first wire is B plus Y, and Y goes from 0 up to H. For the second wire, the magnetic field is in the minus Z direction as I mentioned, and the distance from that wire is A plus B plus Y. Okay, this is the net magnetic field at every point on the surface of this second coil. We want to calculate the flux. Calculating the flux means you integrate the magnetic field of the first infinitely long rectangular coil over the surface S2, which is this one here, of the second coil. So the integral of B1 dot ds. If this is Y and this is Z, then this is X here. Okay, then I will have to integrate X from in this direction from 0 up to the length, and I have to integrate Y from 0 up to H. Okay, I think we called this length L in the previous slide. So this length here is called L and this is called H. The integral relative to X is not a problem because nothing here is a function of X. So this will simply give me L. But the integral relative to Y, the integral of 1 over B plus Y dy will give you the ln of B plus Y. Okay, we proceed and carry out the integration of B1 dot ds over the surface of the second smaller rectangular coil. You integrate from 0 up to H, okay, in the Y direction, from 0 up to L in the X direction. Remember that ds, the surface area, is dx dy in the here in the Z direction, and here this one is also in the Z direction. And I took into account that the second wire creates a field in the negative Z. The integral of 1 over B dy, 1 over B plus Y dy, is the ln of B plus Y. Both upper limit H, you get B plus H. Both lower limit 0, you get B. So this gives you ln B plus H over B. You do the same here. The integral of dy over A plus B plus Y is the ln of A plus B plus Y. Both upper limit, you get A plus B plus H. Both lower limit, you get A plus B. Then you get this expression here. So this is the flux that is going through the second small rectangular coil. And by the way, this is a number. This is a number. If you assume that I1 is 1 ampere, I know L, maybe it's 5 millimeters, H is 10 millimeters, B is 3 millimeters, so on. So this is a number. You can calculate that in Webers. Now the flux linkage, by definition, the flux created from the bigger rectangular coil goes through the surface area of the second coil N2 times because it has N2 turns. Then the flux linkage is equal to N2 multiplying psi to 1. Okay, the last step here is simply to calculate the mutual inductance. Mutual inductance by definition is M21 is equal to lambda 21 divided by I1. So then I1 will disappear and you get an answer that's independent of the current. Okay, so this number here tells you if the current I1 starts to change with time, what will be the voltage created in a small cut of the second coil, second smaller coil. And this, again, as I mentioned, is related to Faraday's law, which is something we are going to discuss very soon in class. Time varying magnetic fields give rise to electric field and hence to voltage difference. Okay. One last question, which I'm not going to be solving. I want you to think about it. We have here two solenoids. One of them is way bigger than the other. So this one has N1 turns. It has a length of L1. It has a current I1. And this is a much smaller solenoid. It has N2 turns. It has a length of L2 and the current of I2. The radius of the first one is A. The radius of the second one is B. And you want to calculate the mutual inductance. So here, of course, someone may say, I would like to assume a current I2. If you assume a current I2 going through this loop here, okay, if you assume a current I2, what is going to happen is that you can calculate indeed the magnetic field everywhere. So you can calculate H2, okay, you can calculate B2, but you can see the field. If I were to draw the field has very complex distribution. And it's not going to be easy for you to be able to handle. So let's see. If I draw that magnetic field, look how it looks like. It looks something like this. So you can see the magnetic field, it changes significantly in the cross section of the bigger coil. So calculating it analytically would be extremely difficult. But if you, on the other hand, assumed a current I1, the magnetic field in the solenoid, as we know from our study, is going to be in the it's very concentrated inside the solenoid, and it's going to be in the Z direction. So if this radius here B, if B is way less than A, then you can assume that the magnetic field in the cross section here does not change. So if I just find the magnetic field at the center and then multiply it, magnetic field flux density at the center, and then multiply it by the area. So the integral of B dot ds will give you B multiplying B1 multiplying by B squared. Okay? And then you can proceed to calculate the flux linkage by multiplying by N2, and then you can get the mutual inductance. So here, this is another example of one case where it is easier to calculate the inductance analytically by assuming I1, not assuming I2. Numerically, you get exactly the same answer. But analytically, again, as I said, in an exam, you have to ask yourself, what is the easier way for me to get the mutual inductance?